Hi, I'm Matt Tarabolski, and welcome to my YouTube channel. Today, I want to talk to you about how I created a 3D printed pectus excavatum vacuum bell. What is pectus excavatum? It's a sunken chest. One in about 300 people have it, and it's 3 times more likely to happen to a man. And I have a mild case of it. It doesn't really affect my life or my health, but some people it does. So in severe cases, it can affect heart function, lung function, and you'll need surgery to fix it. In my case, it's purely cosmetic, and things like a vacuum bell or other external mechanical braces or exercise would be sufficient to treat it. I saw these vacuum bells online, and I had just gotten a 3D printer, so I figured I can do better than that. I can make this thing slim, close to the body that you could get it under a shirt, because some of the regimens ask for about 4 hours of wear time per day, which is a lot. And I thought it'd be a cool idea to have it discreet. And so here's the video describing how I went through that process and what my final results were. Here's how I measured the surface of my chest using sunlight, a flower strainer, and a calibration cone. The shape of the cone is the perfect reference and shows nice concentric rings, as would be expected on a topographical map. By counting those rings and knowing the height of the calibration gauge, I can work out exactly the z-distance into the page of each ring. The rings on my chest each represent the same depth as well. I highlighted the fringes with drawing annotations so you can see the primary interference fringes more clearly. I needed to use a discerning eye to ignore other moiré effects related to the grid of pixels that make up a digital image. Where the lines bunch closely together, the slope is steeper, and where they're more spread, that's a flatter area. This technique is called shadow moiré, and I created a demo of how it works in a ray tracing program. I hope it makes it clear exactly how this technique can take surface topology measurements. There are a few key ingredients needed to make this work. 1. Parallel light. The easiest way to get parallel light is to just use direct sunlight. 2. A regularly spaced 2D grid, spray painted black. I used a flower strainer, and the black spray paint really helped to cut the glare and give much clearer fringes. I think something like a laser printed transparency film taped to flat glass would also work pretty well. The third thing I needed to make the measurement was a calibration cone. I made mine 1 centimeter tall with a diameter of 5 centimeters, and I spray painted it black just to cut the glare and get really crisp fringes. The ray tracing program wouldn't allow me to create diffuse surfaces, so I needed to put point light sources at each point where the parallel light would hit the surface of my chest. Then the light scatters from the surface and goes back up through the grate. And so if I turn on the observer, only the points that are seen by that blue dot are illuminated in the ray tracing program. So you can see that there's a big gap in the middle there. So each line is a fringe. So that will appear bright. And then the dark fringes are where no light comes back. So we have dark, light, dark. Then it stays dark all the way across because that is the zero plane of this setup. Now we have another bright fringe, dark fringe, and another bright fringe to round it out. So to be a little more clear, each fringe represents a discrete step in the distance between the grate and the surface. So here you can see the surface is beginning to change away from the zero plane. So we have a fringe and then a dark fringe and a bright fringe again, and it stays bright until the end. The change in height will be proportional to the number of fringes. And you can see that the technique is not capable of measuring changes in height that are smaller than the grid spacing. So the kind of sharp corners are not captured because there aren't enough tiny shadows to resolve that small detail. Now that you know how the shadow moiré effect works, we can exploit it to create a 3D model of my chest. I imported the picture that I've been sharing with you and started tracing a spline for the shape of the pectus bell that I wanted. You can see it's a pretty random shape. It generally follows the shape of examples that I saw online. So I'm now adjusting each point along the surface to match the fringes that I'm counting. I'm going around the profile and counting the fringes as I go around and adjusting their Z height accordingly. And it's a very painstaking manual process, but you can see the shape of a chest forming. And now I want to do a dome shape. So I created a little circle about 20 or 30 millimeters above the surface of the chest. And now I created a loft which will drop a sheet body between the circle and the profile. And here's the final model of the pectus bell. And this is what I'll 3D print and see if it fits. Now it's time for 3D printing. So I split the bell in half and printed it kind of as a blade. So you can see it coming off the printer here. This is the first half. And it printed really clean because I didn't need any supports. So it came out really nice. And here it is, first time fitting on my chest. And I could see the contours were pretty close. I at this point knew that I was going to be able to get something out of this. Now I'm melting the two halves together. So I'm using a heat gun and just remelting that 3D printed plastic and forming a good seal on both sides so that it's airtight and can hold a vacuum. Then I added one last touch of a silicone seal to conform to the chest and hold a better vacuum. Okay, so I've got the fully assembled pectus bell here. It's got the silicone seal around it. I went and did another layer. I added a second port here as well, which this one was sometimes jabbing into my skin and would get blocked. So I put one here. And I upgraded my vacuum device from a hand pump to this pump that I got out of a pore cleansing kind of tool thing, like a vacuum pore cleanser. So the way it works is I turn this on and then I can set the speed with this button, and hopefully you can hear this. And then you fit the bell on the chest, and I got super lucky and this little tube fits perfectly. I didn't have to make any adapters or anything. And if you just give it about 10 seconds, it starts to pull a vacuum. And once it has a vacuum, then it becomes easier for it to continue pulling a vacuum. You get more and more pressure and a better and better seal. And then, yeah, I can feel it now. Yeah. Oh yeah. So it's now pulling at a kind of light vacuum. So because of the hickeys I've been getting, I'm keeping it at a lower pressure. There's just the first setting on this pump. And there you have it. So now that's holding pressure. Now I can turn it off. And it'll hold for a little while. It'll hold much longer than it used to before I put the silicone seal on it. And There you go. Alright, so I've used the pectus bell 2 times in the last 2 days for a half an hour each. And this is what I have to show for it. Big hickey. Okay, now that you've seen the design process, the build process, the testing, I want to sum up and talk about the successes and failures of the project. Let's start with the failures. So the pump is not very low profile. It's kind of very, it doesn't meet the goal yet. So I wanted to move the pump port down to the bottom and 3D print a vacuum channel into the pectus bell here. So it'll pull the vacuum inside the seal, and you could keep a longer tube and maybe have that go down into your pocket or something. The other big issue is the broken blood vessels, the hickey from usage. So this is typical from what I've seen on other YouTube videos or online, but I think it would be better to have some type of pressure control or pressure regulation that would prevent over vacuuming the skin and damaging the skin. Another area of improvement is, how do I make another custom vel? Like, how would I scan someone else's chest? And the way I'm thinking is to use facial recognition scanners on cell phones. Those are pretty ubiquitous these days. I think that could be engineered to create a 3D scan of the chest. Now let's talk about the successes. Overall, I think it was a success. I mean, I got a seal. It had a very nice fit. The pressure was applied in the right therapeutic area. Overall, the cost was low, at least on a per unit basis. This is like $3 worth of PLA. The pump is inexpensive, and it is lower profile than existing units on the market, even with the pump protruding, which could be much improved. And so only time will tell what the real results will be if it turns out to be effective. So like and subscribe the video to get notified when I have another video showing the update in a few months of how it's going. Thanks for watching, and see you next time.